Allez, on va commencer, ça va faire venir les derniers retardataires. Donc on a l'immense plaisir et l'honneur d'accueillir notre dernier keynote speaker, Francois Sillion, donc directeur technique et numérique du CNES. Alors je ne sais pas si je vais avoir le temps de faire tout ton CV, François. Donc François a occupé des fonctions de recherche à l'université Cornell aux US, mais aussi au CNRS, à l'INRIA, des postes de chercheurs invités au MIT, chez Microsoft, et ainsi que professeur chargé de cours à Polytechnique. Tu as suivi le cycle de l'IHEST aussi. Ces recherches ont porté sur les techniques de création d'images de synthèse. Tu as encadré une quinzaine de thèses, publié une centaine d'articles de recherche sur ces sujets, 2 ouvrages sur la simulation de l'éclairage et la modélisation numérique de l'apparence. Tu as reçu le prix Outstanding Technical Contribution Award en 2009 de l'association internationale Eurographics. Et au sein d'INRIA, tu as fondé, dirigé l'équipe Artis, occupé des fonctions de délégué scientifique, directeur de centre de recherche INRIA Rhône-Alpes. Et tu es devenu également directeur général délégué de la science à l'INRIA, où tu as pu développer des mécanismes de soutien, des projets de recherche exploratoires, des programmes transverses. Tu as fondé, tu as contribué aussi à la mise en place du rapport Villani, hein, c'est ça hein,
Plutôt des suites du rapport. Le rapport lui-même, j'y ai pas participé.
Aux suites du rapport Villani. Et tu as fondé en 2019 et dirigé jusqu'en 2021 le centre de recherche Uber Advanced Technology Center, donc de chez Uber Elevates, c'est ça, hein, à Paris, dédié donc aux technologies numériques pour les nouvelles mobilités, et en particulier la mobilité aérienne urbaine. Et donc depuis 2022, tu es le directeur technique et numérique du CNES. Donc merci infiniment d'avoir accepté notre invitation, c'est un vrai plaisir de t'avoir ici. Et tu vas donc nous parler des enjeux et de la place de l'IA dans l'avenir du spatial. Merci beaucoup.
Merci pour la présentation. Ah, alors je suis peut-être pas sur le bon truc là. Qu'est-ce que j'ai fait? Voilà. I think I'll speak in English because I've met some people during lunch who do not speak French. My slides are in French, and I will take questions gladly in any of these 2 languages. So, as was just briefly explained, I've been doing some research myself, but it was a while ago, and now I'm looking at things from some distance. I'm now at CNES, and I will be speaking about artificial intelligence for space systems. I will try to show you a lot of examples, so I have slides that have many images. I will not be commenting everything, so please refrain from trying to read everything that's on the slides. But I hope to convey to you my vision of why some aspects of space systems are critical, maybe not in the usual sense of, life critical, although there are some that are life critical. Alors, I'm probably going the wrong way. Okay, so these are all of the topics that I would like to be briefly touching, and I hope I will have enough time to reach the end. We'll see. So the first application that comes to mind when you think about space and artificial intelligence is all of the Earth observation, because of course AI is very much linked to image processing, understanding, segmenting, and so on. And indeed, there are many applications that rely and make use of space systems and can benefit from one sort of AI or another. And so I'll be showing you first a number of examples. And it might come as a surprise for some people, because CNES is both the French space agency and also a technical center building or contributing to build a number of actual space systems. But we're also looking into downstream usage of space systems and what can be done with all of this data that's coming from space systems. And in fact, that's why I'm now director for technology and digital, and we wanted, through this new labeling of things, of course it's only words, but we wanted to insist on the fact that digital applications that are that make use of space systems are very important. And so this diagram here is showing one of the ambitions of CNES is to be a house where a number of companies, they can be big corporations, they can be medium-sized, they can be startups, research labs, all these people can come to us, and one of our goals, one of our missions is to help them to incorporate the data that comes from space systems into their applications. Oh, sorry. Okay, so just to give you also an example of the very big variety of space images, or when you mention Earth observation, you can be observing the Earth in a variety of wavelengths. So now we have even multispectral instruments on a given satellite, and then you have more specialized satellites imaging through radar, synthetic aperture radar, visible, infrared, near or more or further infrared. You have instruments that try to I don't know how you say this in English, sondage atmospheric, where you try to understand or analyze the composition of the atmosphere and so on. So you have very many sources of data, and the key aspect here is that it's written in small here, but it's important to understand and to qualify the quality and the real meaning of these measurements. You have absolute measurements, and these come from physics, and then you have the data that you're trying to reach or to understand, and this is usually another physical quantity, and then maybe you have models that let you process the raw data to arrive at the refined data. And there's a lot of processing there, and of course you don't want to lose the faithfulness to the actual phenomena while you're doing this. And also hybridation here is very important. You want to rely on different sources of data and have this cross analysis and cross-fertilization of various sources of data. So this is an example just to tell you that there's now a very rapid increase of applications, and so this is in the urban modeling, urban development, and so on. Actually, this morning, I think it was the person from Toulouse Métropole or one of the officials from the local authorities mentioned it, that now they want to do their local development based on data and based on analysis. And so you have, well, I hope that towards the end I'll know how to use this. Okay, so let me come back. Okay, so here again you have a quick snapshot of a variety of applications where you can try to understand heat. When you have concentration of heat during heat waves, for instance, or you can try to look at what happens at night, and if you have light pollution, or any of these things like detecting trees, that can be important also in the way you analyze and plan the development of your cities. You can also have more things that look more like law enforcement or surveillance, so these can lead to a lot of debates, but of course as you observe from space you can notice a lot of things, including changes, because that's one nice thing about satellites and space systems. Usually you have a fairly frequent revisit every few days, or sometimes even more frequently. And so you can see if new things are built, you can see if land usage is changing, if people are doing things that are not allowed, if people are forgetting to declare swimming pools on their properties, whereas they should do it because they're supposed to pay taxes and things like that. And so here you can start to see that, of course, all of the AI techniques that let you analyze, segment, and classify things can be used, of course, for these applications. But perhaps more importantly, there's a big project that's ongoing. It's actually almost reaching its end, but it will be continued in another form. And now with the very high resolution space systems that are available, we can really do a lot more than basically detecting land usage. You can start doing very fine segmentation of buildings. You can start seeing buildings that have, where is it? Like here. You can start having different heights, even within a single building, and you can almost now, we're at the beginning of being able to do fairly refined 3D models of what you see on the ground. And of course, many of the applications of this are still to invent, and it's actually not space players or space actors that will invent these applications. And so that's where we have this role of making this available to people for them to deploy and invent new applications. So another type of application that's very, very commonly mentioned when we think about space is agriculture, because when you start observing in different wavelengths, you can do things that are fairly precise. You can start segmenting, for instance, the types of land usage that you have. So you have two examples here for the continental France and for the island of Guadeloupe, where you can understand what type of vegetation, for instance, is it crops, is it forest, is it built things, and so on. And so this is important for a number of things, and in particular, you'll notice here one thing that's becoming more and more important, that is detecting water, and I'll come back to that. So again, if you think about, okay, there's space data, you can identify a number of things. What can you do with this, and where can AI start helping? Well, you can now correlate these space observations with other sources. So you can have, for instance, knowledge of the meteorology. So if you start coupling this with what you know about the weather, then you can start to analyze somebody help me, le rendement, crop efficiency, or how much you produce per per surface area, and so on. And so this is interesting because, again, as you can see, AI will let us move from raw data that you observe from space to more refined data that is, of course, of interest for various applications. Slightly different from agriculture, you can also do this process of coupling space observed data with other sources of data to understand impacts on the environment. And so here, for instance, the example that's here is the detection of places where people are dumping waste, and we call them, wild, sauvage, I think it says somewhere, or it just says illegal, but okay. Sometimes we say they décharge sauvage. So basically, people use a place that's not designed for that, and they dump waste. And the problem with that, one of the problems, is that then there can be, with rainfall and the way water takes away various pollutants, you can have effects, and they can propagate through space. Well, through space, I mean on Earth, but spatially. And so again, here, you can couple things that are observed from space with a model of water flow on the ground, for instance, and then you can start having new variables and new things that you can observe or produce for people who are in charge of these topics. Okay, so I have many, many examples. I'll go faster through the remaining examples, but this is yet another one where after a flood, the question here was to try and identify vineyards where the plants actually have suffered from being immersed in the water, and this is very time-consuming to go and check each plant individually, and this is important for insurance, for damage assessment, and so on. Here's another example of damage assessment where you can look at what has changed as you come back to an area, either because of natural disasters, like a big flood here. How should I call them? Industrial disasters. This is the harbor in Beirut with the big explosion of a silo, or unfortunately even more man-made examples of war. And so assessing damage again. It's not just a matter of classifying on an image. Of course, you would like to couple this with other sources of information to be able to, again, produce more meaningful data, such as number of people affected, or whether a given area is still reachable, or things like that. Okay, so I'll skip these because these are just other examples of what happens on the coast and what happens when you have a flood inland and so on. I think you get the idea that what I'm saying is you produce data from Earth observation, and then you refine this data thanks to AI, the way you learn, the way you couple it with models to produce more meaningful variables. So I'll just focus quickly on super resolution, because this is something that's not, it's not only for space, it's something that's useful in many, many applications. But just to give you an example of what we do in the space industry. So you have basically two examples here. The question is, how can you, of course, the resolution is limited. Your satellites are, several hundreds of kilometers away. So even with the very, very strong optics, you can come down to a resolution of a few meters, or maybe down to slightly less than 1 meter. And so you basically have two approaches. One here on the left is that you use the largest resolution, the finest resolution, that you have, and you degrade it to produce lower resolution data sets, and then you start training your systems to learn how to go back from the degraded system to the high resolution. The problem is that you're bound to introduce a number of biases while you're doing this, because you are actually producing the data by downsampling and so the other approach here is perhaps even more interesting, is you try to couple different observations by different instruments. So supposedly there's less coupling, there's less correlation between these two observations. They come at different resolutions. And here's an example where we've done this basically by using a first example here, which is a Sentinel-2 image, and you try to, so on the left here, you basically try to increase the resolution by simply adding more pixels, but all you do is the simplest and stupidest thing is that you do some interpolation, so of course you don't gain anything. And here's an image at a higher resolution, but it's actually processed from it's the same area, but seen with a different instrument. So of course the colors and everything have been matched, so it's a bit strange. And here you can see the result of, this time, a machine learning system where essentially you've learned how to go from here to here. But again, you do this starting from two completely different data sets. So here you can see that we can obtain interesting results. And so you might ask, why is it interesting? Why do we want more resolution now that we have satellite images that are basically under a meter of resolution? Well, one example of an interesting usage, as I mentioned earlier, is water management and the management of water as a resource. If you want to evaluate the state of your resources in water, you have to be able to see very fine things, including very small streams of water. And so it's very important to increase the resolution, but also to do this in a meaningful fashion. It's always possible to increase the resolution and to dump, I don't know, any type of noise, slightly better than noise, but something that has some structure, and you'll have a high resolution image that looks good. The problem, again, as you want to do more treatment on this, as you want to extract more meaningful information, is that you want this to be trustable. And here we come back to one of the words that you use a lot, I think, during these 2 days. So the message I want you to take home from this Earth observation sequence is that, in a way, what's critical there, it's not a life-critical system. It's not a system where things are in danger, or people are in danger, or even the systems themselves. But it's a problem where the quality of the data, as you refine it and as you process it, is very important, because the data is only a means to create applications, provide data to people who make decisions, and so on. And so if all you do is generate data, but it's not trustable, you've lost the point, essentially. So it's one way of being critical, I think. Now let me talk a little bit about artificial intelligence for surveillance or safety, in the sense of space safety. So I'll mention briefly these three topics. First, so let's see if I can play the video. Maybe if you can just reach and play it. Yes, thank you. So here you have an example of a solar event where you have an ejection of coronal mass. And you will see here, as this reaches the Lagrange point, L1, where you have a number of space systems, you see here the name of the systems that have been affected by this event. And so you see that all sorts of systems, some that are at the Lagrange points, some that are on various orbits around the Earth, and even some that are very far away, orbiting around Mars, or trying to reach asteroids and things like that. All of the systems that are mentioned here have actually, this is a real example, have actually suffered from this event, meaning that basically their systems maybe put them in safety mode so that they were not actually usable for a matter of hours or sometimes days because of protection against radiation, protection of the instruments, and so on. And so it would be very interesting to be able to predict these events and especially their importance and their magnitude and their effects. The problem is that we do have a number of sensors that are located here at the L1 Lagrange point between Earth and the Sun, but this is actually quite close to Earth. So by the time the plasma actually reaches the Lagrange point, you have 1 or 2 hours before it reaches the Earth. And so essentially, you know that it's a big bag of ions and high energy particles that's going to reach the Earth. It can have effects on telecommunications, on various systems, so you'd like to have as much advance warning as possible. So 1 or 2 hours of advance warning is not really enough to propagate this information so that people can take appropriate measures or countermeasures. The thing is, this plasma actually takes 2 to 5 days to reach the Lagrange point. So if you could use observations, with electromagnetic waves, so these come in a matter of minutes from the sun, if you can observe the sun and predict that there will be an impact, then you have that much time actually before it reaches the Earth. Now the problem is it's not easy to do, because it's not because you see a spot or you see a flare on the sun. It's actually quite difficult to translate this into the prediction of an effect on Earth. For that, you need a number of models. You need a model of how the coronal mass ejection propagates. You need models of the solar wind. You need all sorts of models. And so one possibility maybe is to use AI in the form of some neural network to basically learn how you can correlate and therefore predict from the observations on the sun that are typically done by the instruments at the L1 point, and what happens 2 to 5 days later in terms of plasma. So this is a very clear example of how we can use AI for space safety. Another example, so I don't know if it's really safety, but I put it there because we have a mission, for instance, that's being prepared now. I think you've all heard about the DART mission from NASA, where they sent an impactor on an asteroid. And so there's a follow-on to that, the Hera mission from the European Space Agency, that will go to the same asteroid and try to characterize the effect of this impact. Look at the crater, do various measurements to understand exactly, very precisely, what the impact was. As you do this, not to say that it's easy, that what NASA did is easy, because it's not easy to find something and smash against an asteroid. But now the question becomes how you go and basically orbit around a very small sized object that you don't know, because right now, the observations of this asteroid are typically, a few pixels in the best images that we have. And so we don't know exactly how to orbit. So we have to figure out all this as we approach it. So it's a little bit like SLAM, where you have to simultaneously build a model of the environment as you approach it, and therefore navigate this environment. So this is another example where typically it's more similar to autonomous driving or whatever, but it's a very weird road where what you have to map is in fact the gravitational field around the object. And the last aspect of space safety, you might think first that it's very far from artificial intelligence, but we at CNES at CNES have a mission for that. It's the safety in the sense of preventing, for instance, the risk of collision in space. We have hundreds of active objects and thousands of objects, and if you had all of the debris and little things that, actually some of them are quite big, that live up there, it's very important to be able to follow them and predict the risk of collision. And here it's a real trade-off, because you cannot be too conservative, because what happens when you have a collision risk? Typically you'll have a maneuver to avoid or to reduce this risk, but this consumes fuel that's available in fixed quantity or limited quantity on board, and so it can reduce if you do it too frequently. First of all, it's difficult. It involves a lot of manual recalculations and so on, and it takes time for people to do this. It's expensive, but also you tend to reduce the length or the effective length of your mission, and so you want to do it only when it's really important. And there was actually a challenge a few years ago. I think there's a new one being prepared, but I haven't heard very precisely, so I hope, in fact, that the new one will happen soon, where the European Space Agency organized a challenge to see if machine learning approaches could actually help by looking at a catalog of events that were observed in the past and see if ML systems were actually able to do good quality predictions. And interestingly, it wasn't very conclusive. So in some cases, for some events, they were very well mapped by the learning systems, and in fact, they were able to predict. But overall, if you look at some average measure, it's not very clear. And so the conclusion was that it's not actually providing a large-scale benefit. I tend to think that there's no reason that we can't do better. So I think that's an area for future work. But it just shows that, you know, the data is very scarce, very limited, fairly low precision. So of course it's difficult to extract a meaningful signal from there. Okay, let me talk a little bit about autonomy. And I mentioned these three topics, three different ways of looking at autonomy in a way. But before I do that, maybe what I'd like to do is say that for the space safety aspect, the criticality of the systems and the missions no longer lies with the quality of the data. It lies with the integrity of the systems themselves, or the integrity of the observation systems of Earth. when we look at collision with asteroids or objects, or the satellites and space systems themselves. Now we'll see a little more, especially when I speak about exploration, criticality in the sense of protecting humans, astronauts, for instance. So let me start by this notion of autonomy. It's very important. It's especially important in space because communicating with the cloud or your base is especially difficult. It's difficult because even if you're in low Earth orbit, you're still, you know, a number of hundreds of kilometers away from the surface of the Earth, and you also have a fast-moving orbit with respect to the ground. That's the difference with being in geostationary orbit, of course. And so you only see the receiving antennas, you know, for a few minutes at a time, and so you have to, it's very difficult and painful to communicate. But you have to communicate, of course. If we send things to space, the ultimate goal is to get something back on Earth. So you have to communicate, but it's expensive, it's complicated, it's difficult. Sometimes it's also very long. If you start sending rovers on Mars, or recently we sent the JUICE mission to Jupiter, you start having communication times that measure in minutes, so it's very difficult to do anything complicated by having a live link. So basically all of these communication arrows here can benefit from some sort of autonomy. This morning Luc Julia very eloquently mentioned the different levels of autonomy, and so I'm not even going to level 5 here. Oops! Which is good because we'll never reach level 5, right? At least for cars. But for space systems, we're very, very low. We're certainly not at the scale of things that you see on cars on Earth right now. The only thing we're doing right now on systems that are live and operating is to try and improve the way we treat the data on board. But that's all. So, and the next 2 slides are the ones with the most text on it. So please do not read it. I will just briefly mention it. But first of all, why do we want autonomy? I mentioned the difficulty of communication because of the delay and because of the difficulty in orienting things and planning the communication times. So one thing that may not be obvious to many people, but for us at CNES it's important because we actually operate a number of space systems, is to optimize the relationship between human operators and the space systems. Right now it's actually a very labor intensive. If you've looked at images, if you've seen images of control centers for space systems, you usually have a big room, like twice the size of this room, full of people working on different aspects on their computers and monitoring data. And monitoring data, using a human operator to just monitor data waiting for something to happen is not a good use of human cognitive systems. And it's something that can be done much more efficiently by, of course, machines. But of course, the question is, we want final control for the human. It's actually similar to the military applications. We want the human in the loop, absolutely. And again, it's critical because we do not want to miss something. Okay, I mentioned the autonomy a little bit when the communication with the ground is not possible or is too slow. Okay, and an important aspect also is to augment the availability of the space systems by doing as much processing as possible on board. Because right now, as I said, we want very predictable and very dumb systems in a way up there, and all of the intelligence is on the ground. Because right now on modern systems, you can actually modify or upload a new version of the flight software on the satellite, but no one likes to do this. You know, when you do this, you're very tense. You know you cannot miss anything, and we're lacking, actually, I'll come back to that, but we're lacking some of the verification and reassuring tools that would let us really trust what's happening. So this is really, there's room for improvement there. And again, in terms of data, as you do some processing up there, you can reduce significantly the amount of data that you have to send down to the ground. If nothing has changed, for instance, since the last time you went over a given region, there's no need to send the same image. Or you can better use the bandwidth by sending maybe more precise information on a particular area. So how do we reach autonomy? I mentioned here a number of possibilities, of avenues. So coordinating several actors is one way. One way that's of course obvious for you, but it's not necessarily obvious for people in the space domain is really to always look at the environment of a system. There's been a tendency in the past, it's changing, but to really have a very principled, if Luc Julia was still here, he would say French engineer approach, maybe to segment things into subsystems, and subsystems would do their job and not know anything about the rest. I think if we want to reach autonomy, we want to have more intelligence, and intelligence means in particular adapting or exchanging data, information about the state of the thing, so that you can have a more informed and complete view of your system. Okay, the one thing I want, the third one was really about being able to learn, but also being able to work hand in hand, if I may say, with humans and AI systems. This is important, as I mentioned the military briefly, where they really insist that control should be finally done by humans. It's the same for space systems, at least for now. So it's important to really work on this interface. And this brings me to one of the topics that you're discussing extensively, which is trust and explainability. So actually one word disappeared here, but Yann Lequin actually about explainability, as you know, is not always convinced that we need to explain, but we need to be able to prove that things, and we've heard a lot about this today, to prove that the result is principled and is of good quality. That's perhaps even more important than explaining, but this is, I'm sure, a topic for further discussion around coffee. So, 3 examples of autonomy. The first one, I will not comment the images here, but just to tell you that we are working on automating and making more autonomous. Therefore, many aspects of navigation. J'ai un trou, GNC, c'est guidance. Okay, guidance, navigation, and control. What you'll mention is that each of these things here is actually what we call R&T, so it's research, technological research. So this tells you that it's not operating yet. It's things that we're working on to prepare the next generation of space systems. For instance, being able to navigate around an asteroid, as I mentioned for the Hera mission. Being able to have more precise positioning. This is something that we're still trying to refine. You know how expensive and how long it is to deploy a constellation of navigation satellites. We're not going to launch a next generation Galileo every 10 years. So there are really ways to improve actually and do more elaborate signal processing in software to even improve the accuracy. And here, this is something again about how you autonomously decide what and how, what data and when you're going to download from your space systems. This is already difficult for one satellite. As you start having constellations and maybe some inter-satellite communication, it becomes a very, very complex problem. Okay, so I'll skip that one because it's not very interesting. Let me mention one aspect that we've developed at CNES, a system that's called Nostradamus. So it's making predictions. And first of all, let me tell you how we do to monitor when we operate a satellite in orbit, how we monitor its functions and how we detect anomalies. So one thing that's being done on board, basically you have sensors that look at whatever, temperature, voltage, you name it, a number of things. And you have a system of thresholds, basically, when you fall below or above a certain threshold, you know that something is not operating properly. And then you have a number of actions, but they're typically hardwired. So the satellite, at the extreme, the satellite can go into safety mode, survie. I'm sorry, I'm missing some word. Survival mode, yes. So everything's shut down and basically you're waiting until you understand more to restart things. But you can have other actions like turning off some instruments, reducing the voltage and maybe degrading slightly the performance. But all this is hardwired. The thing is, it's on board and it can be done very quickly, so it can be done almost immediately. Then on the ground, so what passage means here is the time when we're actually communicating with the satellite, because I'm not sure if everyone knows this, but if you're in low Earth orbit, as I mentioned earlier, it's only, maybe between 3 and 12 times a day that you'll be communicating during a few minutes with your satellite. You don't have a constant and permanent connection. So as we are communicating with the satellite, there can be maybe queries. We can ask questions. We can ask for a precise measurement of a given data that's not automatically and systematically transferred. And then we can do some more complex treatments. And then every month or so, people are looking at all the data that they have gathered, and they're trying to identify long-term things like here you can see, for instance, a drift. You can see the noise that's increasing. None of this would generate, would trigger an action because you're far away from the thresholds, but still you can start analyzing and understanding and maybe preparing for something to happen. So what Nostradamus does is it has two modes, a learning mode and then a surveillance or monitoring mode. And you can really, as you're learning, start learning about the evolution of all the parameters on board. And for instance, something like this, where you have a low threshold and a high threshold, and you have some quantity, I don't know what it is here, well, it's a temperature apparently, and you can see that here something is happening. It's not critical, it's not making you approach one of the thresholds, but still it can tell you that something is happening. And that's where detection systems are important, because then of course you can, first of all, you can, as you learn and across time, you can become more and more knowledgeable, and therefore you can maybe trigger things more automatically. But also you can, of course, send an alert to humans, to operators. So here I have a number of systems, basically 2 of them at CNES. That's the important thing. We've developed 2 of them that are operating right now. And everyone is starting to do this, be it NASA, ESA, and so on. They each have now their own monitoring systems, and that's really a very active field of development. Okay, and lastly, for exploration, it's important, of course, to be autonomous, to react to things that are not planned. So as we go to different planets, different bodies like asteroids and so on, you cannot plan everything. You cannot even locate yourself very precisely. There's no GPS on Mars, not even around the moon for now. So of course it's important. And as you want to coordinate several objects, when we start having several objects on the surface of the moon, for instance, they will have to be able to connect, for instance, or coordinate their actions. If you think about building, for instance, building habitat using robots, of course you will need autonomy there. But it's not really specific to space. The thing that's specific is that you don't really have the backup of transferring control to a ground system, because you have this latency and this difficulty in communication. So you really have, once you send your system, it's basically it has to operate on its own. Okay, so I just want to show you very briefly, speaking of exploration, this is something called a spaceship. So it's an effort, a European effort, to think about how we can approach sending people. You know that for now, Europe is not autonomous in terms of sending people in space, not even in low Earth orbit, of course, we don't have access. So we're even further away from sending people to the moon or Mars or so on. And so the idea of the spaceship is to look at a number of aspects that can range from food and how you protect people from radiation and how you entertain people and so on, and health, of course. And the idea is to test this in low Earth orbit, like on the space station, then on the moon, and ultimately, in a few years, be able to have a permanent or semi-permanent habitat on Mars. So we're actually quite far away, and to be honest, we're far behind the US for sure. China, it's more difficult to know, but in our preparation for that. But the important point there, and that's the slide I wanted to get to, is that in thinking about this spaceship effort, AI is actually in many of these problems. So it's identified here as a problem itself. I don't know exactly why, actually, but it's also present in many things, like how do you supervise a very complex system? How autonomy is there, of course. The idea of training and building metaverses for training, of course. Digital twins, I did not mention it, but it's also, of course, very important to use AI and learning systems to have more efficient simulations and computations. In space, we make extensive use of computations for computational fluid dynamics for rockets, for instance. And of course, as you want to explore new designs, you don't want to do the full-scale simulations and physical simulations for all the parameters. So you want to have, and you all know, I'm sure, how difficult it is. We all would like to have systems that learn from very high fidelity simulations and then can help us roughly map the parameter space so that we know that in some areas it's going to diverge or it's going to be inefficient. And of course, as needed, redo the high performance and high fidelity calculations. So this is something that's also very important. How much more time do I have? 2 minutes. Okay. So I will skip this. Not that it's not interesting, but I just wanted to say that it's important also for people, for astronauts, and that AI can assist astronauts. And I will briefly tell you how we approach at CNES. So as we are a technical center building systems, we of course would like to use deep learning as an example, but any other type of learning or AI, we would like to incorporate it. As you know, it's actually only the same problem that was mentioned this morning for autonomous cars, but only squared or even more difficult, because it doesn't take 5 years to build a satellite or a space system. It takes more like 10 years. And so the processing power and the processing capacity is even further behind. So how do you embed AI on board is really something very difficult. And with the advent of what we call the new space, so smaller companies or companies that are not established or pure space players, companies that want to very quickly develop a service and therefore make use, but they really see it as a commodity, make use of the space systems. These companies typically do not have the financial strength to invest in the very long term. They want to produce things very quickly, maybe even disposable things that you send to space, acquire data for a few months, and then let it die. And so people are starting to use basically off-the-shelf systems. It's a big departure because it used to be the case that you only wanted, and especially when space was mostly geostationary, you wanted to have things that were very much hardened to resist the very difficult radiation environment. Now we're starting to use off-the-shelf things, components that are made for cars and so on, and it's really a big change. So it's both an opportunity because, well, maybe we can use things from autonomous cars, but it's also difficult, and still there's this notion of reducing the size and the complexity of what we put on our systems up there. And so one thing that's very important, and I count on you to invent the solutions, is once you have trained the system and you've built your CNN or whatever, how do you actually make it smaller by pruning or distillating or reducing it to something that has a lower footprint so that you can actually use it in these systems. And here is just an example where you can go from basically going from 32-bit precision to 4-bit precision and retaining the good detection accuracy. And I think I'll probably, excuse me for the fast, let me just finish with my last slide here that I think is important. All these applications and the things that I mentioned are anchored in the space domain in the sense that we're building space systems, but very few of them are specific to space. And so the cooperation and the fact that the things that we're using, I mentioned the super resolution, for instance, they can be and they will be developed by people who are much smarter than we are and who are like you, like you people. And I really strongly believe it's important for us to explain what our problems are, what is critical for us, so that maybe this can be taken into account in the algorithms and the things that are investigated by research. And that's basically the best we can do. We're not going to compete with people specialized in AI and reinvent the wheel. So for instance, one thing we've done, it was actually during the pandemic, is work with the local hospital. And it's actually interesting that at first people inside CNES said, why are you working with a hospital? You're wasting time, you're not working on space systems. In fact, it turns out that it can be important when you start thinking about sending astronauts on Mars, they will have to be able to perform advanced medical gestures and analysis, and so it will be important for them to have advanced systems. But I think this cooperation aspect is very important. And I might add on a personal note that I've been doing 25 years of research myself at INRIA, and then I built this research center for Uber Elevate, where the idea was to incorporate flying machines on the Uber platform. And what I discovered there is that there's really, it's really in the transfer from this research to very practical things. We mentioned at the end of the morning also the problems of certification for flying objects with EASA and so on. There's really a hard part. As you go, you invent very, very capable algorithms. I've seen some very interesting posters outside. Adapting this and explaining and convincing the people who are from a given industry is a challenge in itself. And so it requires patience and a lot of discussion. So I hope a conference like this one can be a good opportunity. Thank you.
Thank you so much, Francois. I agree with you with this need for synergies, cooperations between sectors. It's so important. Time for one or two questions only.
Thank you very much for your presentation. You mentioned about the water management based on the satellite images. Would you mind give a little bit more information what exactly that is for?
Oh, well, one aspect is, well, one thing that can be done, for instance, is measuring. It can be done, maybe I'm going a bit too far. We're starting to see that it could be done. Is measuring very accurately the water level in a number of situations. So you might know that, for instance, in December of 2022 was launched the SWOT mission. It's a mission from NASA and CNES actually, and also the UK Space Agency. And it's really the goal of this system is to measure the altitude of a water surface. So the primary objective is on the ocean. That's very important for modeling, for climate models and so on, but also for continental water, because we're starting to have resolutions that will let us measure things that are, the objective was 50 to 100 meter wide, so large rivers. In fact, the first images of Toulouse, for instance, show that even the Canal du Midi, so the canal that runs through the city, can be imaged. So only, maybe 20 meters. As you start being able to measure the level of waterways, you can estimate the amount of water that's circulating. So the applications can be in predicting, for instance, droughts and the way the water levels evolve for agriculture. It can be used also for very political or geopolitical aspects. In many cases, there are frontiers between countries that share a given river, and they usually have agreements on how much they can drain from that, and usually they fight over that. There's actually a number of examples right now as I speak. And so these tools can actually help for that. They can also help when water is used for a variety of things, like producing electricity, because you know that there you need to plan how much water you're going to release. Also for power plants that use maybe a lot of water. So if you know that there's water coming, you can better plan how you can use your power plant and so on.
One more question.
Yeah, you told us that we could take benefit from other domains in terms of AI, but are you optimistic about the ESSS standard evolvement, because they are many rely on rules and something that easy to prove. And here, even if we want to embed your Nostradamus tool on board, are you sure that ESSS standards will evolve only in 10 years, for instance?
Alors, am I sure? I'm reasonably sure. I'm definitely optimistic. And let me take the example of aviation, where we're seeing it takes time. 5 years ago, I remember discussions with people from an agency that I will not name, but a French agency that deals with civil aviation. And they were saying there's no way we're ever going to certify or accept something that has machine learning in it. Because, and the reason was, because it's non-deterministic. I was surprised. I tried to argue. I said, well, once you've learned something and you've built your system, it is deterministic. Maybe you cannot explain, or you know all this better than I do. We're seeing things evolve, I think. And so now it's no longer taboo, you're no longer being escorted out of the room if you mention automating air traffic, for instance, and things like that. So yes, I'm optimistic, but I think 10 years is definitely the approximate scale at which these things can evolve. Certainly not less than 10 years.
Thanks.
I have a last question, very similar to yours, about taking risks. Putting AI in the system is often synonym of taking some risk. Some companies are taking this kind of risks. Well, we mentioned one this morning. What is your personal feeling about the ability of the French space sector to take this kind of risk?
Okay, is this recorded?
Stop recording.
Well, no, I'm smiling because it is a fact that, for instance, CNES is a public agency, and so the government, which is our boss, tells us that we should take more risks, and that we should help a culture of risk to disseminate. And it's similar to what Luc Julia said this morning. We'll try things, and maybe it fails, but we learn things, and so on. All this is very true, but let me tell you that if the first flight of Ariane 6 fails, you will not find anyone in government that will say, oh yes, but we want to take risks. So there's definitely a question of culture. Now, that being said, it is the case that many of the new companies that are arriving do have a different approach. So maybe one way, and I know that everyone is talking about this at ESA, for instance, the European Space Agency, but also in the big industrial companies, trying to segment basically space systems and classify them into really critical systems where failure is not an option, and going all the way to what I mentioned earlier, maybe almost disposable systems where you throw it in the air. If it works, fine. If it doesn't work, you just change a little thing and do it again. And so for that, maybe it will be also differentiated standards and ECSS and things like that, and that will be, I think, the avenue for taking more risks. But definitely, it's not part of the culture, and it's not part of the culture of the people who finance these systems right now in France to take risks. And anytime there's a failure, like Elon Musk tweet, "This is great. I have a ton of data, and I can do better next time." Yeah.
Thank you very much. Thank you, François.